Here goes my first video using the iPad. This could be a disaster or not. Anyway, the idea here is for me to do blurting. Thought I'll try a different way of doing it, partly because I haven't got any way of holding my phone at home. So, line spectra, quite a good topic for blurting. There's actually quite a lot to know. We'll start right at the beginning. We need a glass tube. That's what was that meant to be. We need a high voltage, and then we have some gas in here, and because of the gas in there, electrons are accelerated down that tube, and we have atoms, and we have electrons, and the accelerated electrons collide with an electron in the atom, and this can either cause an excitation or it can cause an ionization. So we'll draw little diagrams for these, but ionization is the total removal of an electron if there's sufficient energy. Excitation is moving to a higher energy level. So we can represent the energy levels in an atom as a set of lines like this. So it's a bit of a confusing diagram because there are no literal lines in the atom. The electron is just around the atom. These simply represents the amounts of energy. The top one is at zero energy, and all the others are at a minus energy. For simplicity, I'm going to label mine in electron volts, and the normal thing applies that 1 electron volt is 1.6 times 10 to the minus 19 joules. Notice the minus, that's because we suddenly understand this for the first time because we've done our work on electrical potential. And we now know that for a system where there's an attraction, so there's an attraction between the negative electron and the positive nucleus, we have less energy with the electron near the nucleus of the atom than we do out in infinity or far, far away. So all energies are negative. So if an excitation occurs, the electron is moved to a higher energy level. If an ionization occurs, that means effectively the electron can get to far, far away. And in this case, the minimum energy for an ionization would be 14 electron volts to take it up to the zero level. If an excitation occurs, that's an unstable situation. So our electron will want to return to the ground level, to the n equals 0 state, which is the only place where it's stable. How does it get rid of its energy? It will give out energy in the form of a photon. It doesn't have to go right back in one go. It could go back via a smaller jump, and a smaller jump will reduce in a longer wavelength photon. So if we just have a quick reminder, the electromagnetic spectrum simplified: red, green, blue. So this is long wavelength. No, it isn't. That is short wavelength. This is long wavelength, but these are high energy photons, and these are low energy photons. And this is the low frequency, and this is the high frequency. So big gaps, high energy photons, higher frequency radiation, shorter wavelength, and higher energy photons. What are our practical applications for this? Well, we might view a line spectra. So we've passed our line through a diffraction grating, and we just see a set of allowed lines, and that's evidence for the energy levels in the atom, with each one of these lines corresponding to a movement between two separate energy levels, so we can identify unknown elements. We can also identify gases in stars. We just need to talk about another step here. So this was excitation by the absorption of an electron. So let's just draw that again. And the thing here is that, say our electron comes in with energy 8 electron volts. And to cause an excitation, we need to go from, I don't know, minus 14 eV to minus 9 eV. We need 5 electron volts of energy, don't we? Just trying to keep the numbers sensible. So that means our electron can zip off with 3 electron volts, and that will leave 5 electron volts over to cause our excitation. So provided the electron has sufficient energy, the excitation can occur. That's different to excitation by a photon. If we have exactly the same atom, and this time in comes a photon, and the one photon interacts with one electron in the atom, and it's carrying 8 electron volts, nothing happens, assuming there's not another energy level up here at exactly 8 electron volts, because the photon has to give all its energy to that electron. That means it would move it up 8 electron volts, but if there's no energy level for it to sit in, then it can't go and nothing happens. So electrons just have to have sufficient energy, photons have to have exact energy, and that leads to this idea of an absorption spectra. If we have some gas and then we shine in white light, so a complete mixture of all wavelengths, then I'm just going to get a really fat pen. What's going to happen is that we end up with a spectrum. Okay, see if we can draw. So red, blue, green. This isn't going to be the world's greatest spectrum, but it will make the idea. So that's all of our white light. Why don't you click on there? Here we go. That's all of our white light coming through. But if a photon in the white light happens to meet a electron in an atom and have exactly the right energy to cause an excitation, it will be absorbed. So whereas the emission spectrum, emission being given out, is dark with bright bands, should have drawn that with a black background, but never mind. An absorption spectra is bright with black lines, and each black line represents a possible absorption. And that's what we see in starlight. The star is over here. It's showing out white light. The atoms in the atmosphere absorb specific energies of photons, and that leaves gaps in the spectrum, and this is called an absorption spectra. And that's how we know, for example, that the sun is made out of hydrogen and helium, and we know there are other stars with other elements in them. You might say very cleverly, and you'd be right, well, if this blue photon came in, caused an excitation, well, why, when it was re-emitted, when there was a de-excitation, why wasn't it sent back? Why didn't we see it? Why is it missing in our spectrum? And the answer is simply the chances are it goes off in a different direction and we don't see it. Just a couple more things that sometimes crop up. They like to say give you a number of energy levels, and they say if an electron is here, and they say how many different wavelengths can be produced, or how many different energies of photons. So it can go down any number of energy levels each time. So what we'll do is we'll just count them up. 1, 2, 3. But of course, once we're in that level here, there are 2 more. That can do that, or it can do that. And once we're in that level, we can do that. So that would give 6 possible energies of photons emitted. And then the last thing we have to talk about is the fluorescent tube, which is how the physics labs are illuminated at work. Again, we have a high voltage. Inside here, we have mercury vapour, and that has to have low pressure, and it has to be partly ionised. So why does it have to be partly ionised? Well, and why does it have to be low pressure? So our Earth's little electron is racing down the tube, hoping to cause an excitation. In high pressure gas, the particles, relatively speaking, are close together. Our poor electron only gains a tiny little bit of energy between collisions. In low pressure gas, they're much further apart. They shouldn't be bigger. So it gains more energy between collisions, more likely to have sufficient energy to cause an excitation. And we need electrons to go down the tube. So if the odd atom isn't ionised, we won't have any electrons to accelerate down the tube. So partly ionised, so there are electrons. Low pressure, so the electrons move more distance and gain more energy between collisions. Mercury vapour will only give out UV photons, which is great if you want ultraviolet light, but it's no help whatsoever if you want visible light in a room. So if we examine a cross-section of the tube, that's the glass on the outside. Oh, that's set way too big. I think I better undo that. So I'm just going to draw in green. It's not actually green, it's white, but inside the tube, just inside the tube, is a fluorescent, which even I can do better at spelling fluorescent than that. Coating. Well, I definitely needed an L and an R. I think you don't really, it's a bit of a dull video just watching me trying to... Yeah, that's better. There's a fluorescent powder, now the autocorrect made it look rubbish again. Never mind. The ultraviolet photon is heading out like that. It collides with an electron inside the fluorescent powder. The fluorescent powder has much more closely spaced energy levels. So in comes the photon. The electron is promoted to a higher energy level. And as it cascades, it's giving out lower energy photons, which are in the visible part of the spectrum. And because, we can have different size gaps. So if we wanted a blue one, it could still go. The electron could jump from there to there. But the point is we've converted a high energy ultraviolet photon into a low energy visible light. So hardly spectacular in terms of how visually nice that was, but I think that's all the main point covered. I'm just going to check the spelling of the word fluorescent. Floures. Yeah, no, that's great. Okay, folks, thank you.